is notes part 2, starting with the exponential function. Remember what we were doing in our notes previously is we took our calculator out and we went to y equals, and we're going to type in on this particular one e to the x. And notice on your graphing calculator on the keypad that it is the e to the x is above the ln button. So far left side of the calculator, third button up roughly, we're going to press second and then ln to get the e. We have to type in the x. And we look at the picture when we hit graph. And there's a picture. A couple things to remember from our previous notes is even though our calculator, this graph looks like it touches the x-axis, it doesn't really touch the x-axis. It's getting closer and closer and closer to the x-axis, but it doesn't quite touch. And then what we did is we wanted to come up with a couple key points, so we went to our table, and I think I have some extra points left up there, so I'm going to change that, but I'm going to go to second in table set, and I'm going to go in increments of 1 here, which is what I just put in. Change in table is 1, to maybe get some better values here. And in general, I like to graph points that are whole number points. It is not possible on this function. So I left 4 spaces on your table. And the values here that I am going to graph are -1 and 0.37. 0, 1, there's a nice point for us to work with. 1, 2.7, and 2, 7.4. And then we're going to draw the picture. And again, you can always go back and look at your calculator to see that particular picture. What does the graph look like? Just by hitting the graph. So we see that. Do the best you can. Sometimes the board is not as oriented as I want it to be, but it's -1, 0.37, 0, 1, 1, 2.7, and 2, 7.4. 1, 2, 3, 4, 5, 6, 7. And my picture there is a little bit better than what we saw on the graphing calculator. And the other piece of information that we need to identify here from our exponential function is we want to identify the domain and the range. Remember that the domain deals with the x values. And what we can see is that we're completely above the x-axis, although we don't have any limitation. We can pick any value for x, whether it be a positive number, a negative number, a fraction, a decimal, a radical, or 0. So our domain of our functions are real numbers. But again, the graph is completely above the x-axis, and the way that we can say that is that we're going to go from 0 to infinity. 0 is not included. We're above the x-axis. We're not going to touch the x-axis, even though our calculator looks like it does. It doesn't really. Also remember, we're going to leave even, odd, neither 1 to 1 for later. But here's our exponential function. Our next graph is going to be the logarithmic function. There should be a button to the left on your calculator, again for the logarithmic function. And if we pull this up, here, deleting the previous graph. Again, the fourth button from the left up is the log, and then log of x. If you're using an Inspire, I learned today that the Inspire calculator might have you put something in here. There's a box beside the log, but apparently if you don't type anything in, it assumes the value to be 10, which it is. But if it wants you to type something in, type in 10 for you Inspire users. But once we get this, again, let's look at the picture. And remember, the calculator is limited on its graphics. So there's the picture, but it does continue down, but it doesn't touch the y-axis. The graph doesn't touch the y-axis. If we go to our table, I am gonna try to change my table value a little bit here. Back to what it was originally, which is if I go to second and the window button, that gets the table set. I'm going to leave it -2, but I'm going to put it back in increments of 1/2. And then, if I can, look at some values on the table. And the reason that I wanted to change our increment a little bit is just to get this 0.5 negative 0.301. And now we can fill in. It's 0.5 negative 0.301 10. A couple other values that I put in here, or one more value that I put in here was 10.1. I don't want to scroll down through my screen right now with the smart board being temperamental so much. But if you scroll down on your screen, you will see that value of 10.1. And whenever possible, I try to graph points that are more precise, if I can. But I wanted that half, the 0.5, and the negative 0.301, and then the 1, 0, and then the 10, 1. And I gotta draw that one again. 0.5, negative 0.301, 1, 1, 10, 1. A lot better. And what we can see on this particular graph as you're graphing it is it's everything to the right of the y-axis, and that means that our x values are only going to be from 0 to infinity, and 0 is not included. So it's going to be from 0 to infinity, because our graph, even though it doesn't show up so well on the calculator, is getting closer and closer and closer to the y-axis, but is not quite touching. Now what we can also see is that our y values in here, we don't have any restrictions on them. We've got positive values, we've got negative values, we've got 0. Our range of this function is all real numbers. Let's fix this. Infinity never has a square bracket. Infinity only has a parentheses. And now we've got our domain 0 to infinity and our range negative infinity to infinity. So the last one was called a logarithmic function. This next one is called a natural log function. It comes from the French, and if you've ever taken French before, you know that compared to English, sometimes they reverse the order of their words. So what they would say in French is they'd say logarithmic natural instead of, for us, natural log. So logarithmic starts with L, natural starts with N. There's where the LN comes from. We've seen that button already today because we saw it when we graphed the exponential function at the top of this page. So we know where that button is on our calculator. So we can go back to our y equals. And this time, instead of log, we're going to type in the natural log, which is ln, one button below it, and x. And it's always nice to know what does the picture look like. Again, our screen a little bit limited, but we get the general idea of this. And once we've got the picture, we can go to our table and come up with a couple points to use. And again, I'm going to be limited in terms of nice points to work with. Nice points mean whole number points to work with. Don't have that option. But what we've got here is we've got our 0.5, 0.5, negative 0.7, 1, 0. Then I actually did 5 and 1.6, which you got to scroll down on your calculator for. And I did 10, 2.3. Just to get us going a little bit in the right direction, giving us some points that are spread out so we can fit it in our graph, or at least we can get a good picture. So when we graph 0.5, negative 7, 1, 0, 5 is 1.6, try that one more time, and 10 is 2.3. And just like the previous logarithmic function, we are not going to touch the y-axis. So the nice part is, when we look up above at the logarithmic function, our domain and range are going to be the same. We're limited on the domain. We can only go from 0 to infinity, both of them having parentheses, because we're never going to touch the y-axis. But our range, our y values, we're not going to be limited on those. It's going to be from negative infinity to infinity. The next function is called the greatest integer function. And I know there's a lot on the screen, and it's not quite as complicated as it looks. But on the calculator like I have on my screen, which is just the TI-84, what we need to do is we need to go back to y equals, and then we're going to clear out the natural log of x, and we're going to type in the greatest integer function. On the Inspires, it's called the floor function. But in order to get to that on this particular calculator that we have up here on the board, we're going to go to Math. We're going to arrow over to Number. And then it's going to be number 5 in this screen. And then we type in your x. Greatest integer function. When I learned about these particular functions, they were called step functions. And one of the reasons that they're called step functions is because our graph looks like a bunch of stair steps. If we look at our table here, we can get a couple of points to put on our graph. But what we see is we've got -1, -1, -0.5, -1, 0, 0, 0.5, 0, 1, 1. Well, we need to think about this a little bit more, and I want to look at these tables here of really what's happening a little bit more closely. And what we can do is, once again, on our calculator, we can go to the table, and what you see is that we're in increments of 0.2. So I'm actually going to start on 0 here for this one and go in increments of 0.2. And then we can look a little bit more carefully at our table. And as I look at this, I need to scroll so that we can match our table to the left there. So what we see is that at -1, we get a value of -1. Looking back at the screen, it's nice that you can look down at your paper there. But looking at the screen there, -0.8, we get -1. -0.6, we get -1. -0.4, we get -1. -0.2, we get -1. And then we get 0. And if we continue to look at our screen, to fill these in, then we've got 0.2, 0.4, 0.6, 0.8. Those are all zeros. And then we go to 1. And then 2. And what's happening really in this table is when we plug a value for x, which by the way, the function is written in these double square brackets. When we plug x back into that function, what happens is that our function rounds each value back to the closest integer. The greatest integer of -0.8 is -1. It's going to be a smaller value. And I think it's easier to see. The greatest integer of 0.2 is 0. The greatest integer of 0.4 is 0. It's the first integer that is not bigger than what you're putting in. So you're not rounding it, because if you get to 0.8, you're not going up to 1. You're going to the first number, that's first integer that's not bigger than 0.8, which is 0. If you go to 1, that's bigger than that. And then, once you know that, what happens is, when you graph these, if we start with this, 0.2 is 0. Actually, 0 is 0. 0.2 is 0. 0.4 is 0. 0.6 is 0. 0.8 is 0. But when you get to the value of 1, you're going to step up. You're going to jump up. So that's where you're going to make your step. And then you do 1.2, 1.4, 1.6, 1.8. And then when you get to 2, you're going to make a step up. And so forth. You get to 2, 2.2, 2.4, 2.6, 2.8, 3. You make a step up. And once you do about 2 or 3 steps, you get a pattern. And not only can you go up the stairs, but you can also go down the stairs. And there's our function. Let me point out again that on a graphing calculator, it's limited. Even the good calculators don't show the open circle, to the best of my knowledge, on their calculator. So there's the greatest integer function. It's usually one that's easy to remember because it's so radically different from the others. Our domain of this function is still negative infinity to infinity, but our range is limited. The steps are at 0, at 1, at 2, at 3, at negative 1, and negative 2, and negative 3. Our range are the integers. Just a couple more. There's, I think, 3 functions left that don't have any names for them. As we go back to our calculator here, I want to do a couple things. I'm going to go to y equals, and I'm going to clear that out. And I'm also going to go to the table set, so I want the second and window. But I do want to leave my window in half increments, so I'm going to start at 0, but I'm going to put it in half increments. And once we get that situated, then we can go to y equals, and this time we can type in our function of 1 over x squared. If you have the calculator, it's always nice to use the fraction button. So look at a graph. And we've seen many today. Our graph, even though it looks like on the screen that it touches the x-axis, the graph doesn't touch the x-axis. We can look at a couple points, and if you can't tell there, the fact that we have some airs is an indication. But as I look at this one, what I see is some values here that I can use for my table to help us graph. Like negative 2.25, negative 1, 1, negative 0.5, 4. And I mostly can do nice points to work with on this one. But then I can also do positive 0.5, 4, 1, 1, and 2.25, and you might have to add that underneath your table. I did as well. But once we have a couple of good points to work with, then we can graph. Negative 2.25. Negative 1, 1. Negative 0.5, 4. There's one branch. And then it's positive 0.5, 4. 1, 1, 2.25. And maybe a little bit better picture on the freehand rather than the screen, only because we can see that our graph does not touch the x-axis. Not only does it not touch the x-axis, but it also doesn't touch the y-axis. And because it doesn't touch the y-axis, we can say that x doesn't equal 0. But the thing about that is all that means for us in integral notation is that negative infinity to 0 joined with 0 to infinity. Sorry, getting disoriented over there. I guess I'm going to try one more time. 0 to infinity. 0, comma, infinity. Better. Our range. Oftentimes when we're dealing with range, we're asking ourselves, do we have a high point, do we have a low point in the graph? Well, our graph never goes below the x-axis, so our range is going to be from 0 to infinity. It doesn't touch the x-axis either, so we're going to have parentheses on there. So no name. 1 over x squared is that function. The next one is very close to it. It's 1 over 1 plus x squared. And let's type it in our calculator. So we go to y equals. Don't have to change too much on here. And definitely, maybe I can and maybe I can't. If you don't have a fraction button, put parentheses around the 1 plus x squared. The 1 plus x squared will need parentheses if you don't have a fraction button. But once we have that, then we can draw the picture. And once again, like the previous problems, we are not touching the x-axis. We can go to the table here, and we can get a couple of points. And in fact, I think I'm going to change my screen one more time again, and go back to our increments of just 1. And what we have here, and I don't know why it suddenly put it in fractions instead of decimals, but it doesn't make any difference when we look at these values here. We have -2, which is 0.2, which is what 1/5 is. -1 is 0.5, which is what 1/2 is as a decimal. 0, 1, +1, and 0.5, which is the same thing as 1/2, and +2 and 0.2, which is the same thing as the 1/5 as a decimal, if you prefer. Once we get a couple key points, we can draw the picture, and we've seen what it looks like already, so we have a good idea. -2.2, -1.5, 0, 1, 1.5, 2.2. There's a picture of 1 divided by 1 plus x squared. And once again, we don't touch the x-axis. But x can be a positive number, it can be a negative number, it can be any value. So our domain is -infinity to infinity. But the graph is strictly above the x-axis, and we've seen that quite a lot today. So we're going to go from 0 to infinity, and there's our graph. As we finish here with this last one, square root of 1 minus x squared. Going back to y equals, clearing that, square root of 1 minus x squared. It's kind of a fun one to graph. That's it. And in terms of points, it's interesting when you look at the table. Lots of errors in there. We only have a few values that we're going to graph. In fact, the 3 that we can see are the 3 key points to me. -1, 0, 0, 1, and +1, 0. So negative 1, 0, 0, 1, 1, 0. So we do touch the x-axis this time. And we can very much identify our domain. Remember that domain or the x values goes from left to right. So our domain is negative 1 to 1. It's going to have square brackets because both those values are on the graph. And our range. Our range is the lowest value to the highest value. Well, our lowest value is 0 and our highest value is 1. And again, those are both on the graph.